My dear students, today we are going to discuss the chemical reactions of alkanes. Previously in my lecture number 1, we have discussed what are the alkanes, what are the functional groups, and how alkanes can be synthesized in the laboratory. So if you have missed this lecture, I suggest you to please consult my first lecture on alkanes and then proceed for this lecture. It will help you a lot. This lecture is made for the fundamental of organic chemistry code Chem 1113 and it is taught to the BS chemistry students of the first semester. Here is a list of the key concepts that you will learn today. In this lecture, we will discuss the combustion of alkanes in addition to the different oxidation methods of alkanes. We will also discuss halogenation reactions of alkanes involving free radical mechanism. We will discuss thermal cracking or pyrolysis of alkanes in addition to the study of sulfonation, nitration, dehydrogenation, and finally we will discuss isomerization and catalytic reforming. So these are the key concepts that we are going to learn today. Are also called paraffins. The literal meaning of paraffin is low affinity. So the meaning of the paraffin is low affinity. This name of alkanes is derived from the very little chemical reactions of alkanes. Alkanes show little chemical affinity for other substances and are chemically and biologically inert. They are inert due to the possession of a strong carbon-carbon single bond and carbon-hydrogen bonds, and due to the absence of functional groups. Alkanes contain strong carbon-carbon single bonds and strong carbon-carbon hydrogen bonds. Both of these bonds are non-polar. Therefore, there is no portion of the molecule that carries any significant amount of positive or negative charge, which is required for other ionic or polar molecules to be attracted to it. Therefore, alkanes generally do not react with ionic compounds such as most laboratory acids, oxidizing agents, or reducing agents. For example, if we consider the example of a butane, butane do not react with base, it will not react with acid, it will not react with KMN. Alkanes are hydrocarbons made up of only carbon and hydrogen atoms. They are saturated where central carbon atom is attached to 4 other atoms or groups. In terms of hybridization, alkanes are sp3, show sp3 hybridization where p orbitals of carbon are overlapping with the s orbitals of hydrogen atoms. This saturation is responsible for relatively low reactivity of alkanes. Traditionally, in old times, saturated hydrocarbons were known as paraffins, meaning little affinity. However, alkanes undergo some important chemical reactions and act as precursors for a series of other chemical products that we will discuss in the coming sections of this lecture. Here, with the example of n-butane, you may see that here, if n-butane is made to react with base, no reaction is observed. This is because of the relative inertness of the carbon-carbon bonds, which are non-polar, and the relative inertness of the carbon-hydrogen bonds, which are also non-polar. If we heat the n-butane with acid, still we observe no reaction. So no reactions are observed when n-butane are heated with acid or base. Similarly, when n-butane is made to react with KMnO4, a strong oxidizing agent, still it gives no reaction. So alkanes are usually retardant or the inert towards the ester bases and the oxidizing. Due to the saturation, reactions of alkanes are mostly targeting carbon-carbon or carbon-hydrogen sigma bonds. The cleavage of these bonds generates some activated species that act as intermediate in chemical reactions. Breaking bond is known as bond dissociation, and the energy required to break a bond is called bond dissociation energy, which is represented with delta H naught. The bond breaking where two bonding electrons are equally divided between the two participating atoms is called homolytic cleavage. Alkanes mostly undergo this type of bond breakage, and as a result of this generate species containing unpaired electrons called free radicals. So the free radicals are the species that possess unpaired electrons, and they are produced or generated because of the homolytic or the hemolytic cleavage of the sigma bonds. In hemolytic cleavage, one species gets one electron and the other species obtain the one single electron. An atom of groups of atoms possessing odd or unpaired electrons are called the free radicals. The energy required for this purpose in the case of alkanes is provided by either light or heat. So here I am emphasizing that the most of the chemical reactions of the alkanes are limited to the carbon-carbon cleavage or carbon-hydrogen cleavage chemical reaction, and mostly these bonds are broken homolytically, and as a result free radicals are formed or generated, which then start a chain reaction. The other important chemical reaction of the alkanes are restricted to the combustion. Combustion needs a flame to get it started, and whereas the halogen reacts with alkanes in the presence of heat or light. Much of the chemistry of alkanes involve free radicals, and chain reactions are involved. Always remember two key points. Energy is always required to break a bond. Energy is always released when a bond is made. So for the breaking of a bond, you need energy. And energy is always released when a new chemical bond is formed. Although each molecule has its own characteristic bond energy, some generalizations are possible. For example, although the exact value of a carbon-hydrogen covalent bond energy depends on the particular molecule, all CH bonds or the carbon-hydrogen covalent bonds have a bond energy of roughly the same value. It takes roughly 100 kilocalories of energy to break 1 mole of carbon-hydrogen sigma bond, so we speak of the bond energy of a carbon-hydrogen bond as being about 100 kilocalorie per mole. A carbon-carbon single bond has an approximate bond energy of 80 kilocalorie per mole, whereas a carbon-carbon double bond has a bond energy of about 145 kilocalorie per mole. We can calculate a more general bond energy by finding the average of bond energies of a specific bond in different molecules to get the average bond energy. This knowledge of bond energies will help us to find out how many energies or how many kilocalories will be obtained when 1 mole of a particular alkane is completely burned in the presence of oxygen. The combustion of carbon compounds, especially hydrocarbons or alkanes, has been the most important source of heat energy for human civilization throughout recorded history. The practical importance of this reaction cannot be denied, but the method and uncontrolled chemical changes that take place in combustion make it difficult to deduce mechanistic paths. Using the combustion of methane as an example, we see from the following equation on this slide that every covalent bond in the reactant or the methane has been broken and an entirely new set of covalent bonds have formed in the products. No other common reactions involved such a profound and pervasive change, and the mechanism of combustion is so complex that chemists are just beginning to explore and understand some of its elementary features. So here you may see that when methane is completely burned, in the presence of oxygen, carbon dioxide and water are produced. One molecule of methane produces one molecule of carbon dioxide and two molecules of water upon reacting with two molecules of oxygen. When 1 mole of methane is completely converted into carbon dioxide and water, 890 kilojoules per mole of energy is obtained. The amount of heat evolved when 1 mole of a hydrocarbon is burned to carbon dioxide and water is called heat of combustion. Note that in this reaction that the compound on the left side of the arrow are called the substrate or the reactants, and the compounds on the right side of the arrow are the products of the reaction. Energy most often released as heat can either be a substrate or the product of the reaction depending on the compounds involved. Also note that none of the atoms are lost within a given chemical equation. The law of conservation of mass states that matter can never be created nor destroyed. Thus, the equation must be balanced and have the same number of each atom on the left side of the equation as on the right side. Chemical bonds also hold potential energy. If you think about the nature of the bond held together by the energy of attraction, to break apart bonds on the reactant side of the equation requires energy, while the formation of the bond on the product side will release the energy. If the energy released by bond formation is higher than that required for bond dissociation, energy will be released by the reaction. This energy is usually measured as heat of reaction, which is called enthalpy. 2 points concerning these reactions are important. Since all the covalent bonds in the reactant molecules are broken, the quantity of heat evolved in this reaction is related to the strength of these bonds, and of course the strength of the bonds formed in the products. These heats can be evaluated using the bond dissociation formation energy. The energy required to break a bond on the reactant side of the equation and the energy released by bond formation on the product side of the equation. The second point of this chemical reaction or the combustion is the stoichiometry of the reactant is also important. If insufficient oxygen is supplied, some of the product will consist of the less oxidized carbon monoxide gas. For example, if methane or the propanes are burned in the limited supply of oxygen, suppose we are burning the propane in the limited supply of oxygen, carbon dioxide and carbon monoxide and water, and heat will be produced. Atoms bond together to form compounds because in doing so they attain lower energies than they possess as individual atoms. A quantity of energy equal to the difference between the energies of the bonded atoms and the energies of the separated atoms is released usually as heat. That is, the bonded atoms have a lower energy than the individual atoms have as separate atoms. When atoms combine to make a compound, energy is always given off and the compound has a lower overall energy. When a chemical reaction occurs, molecular bonds are broken and other bonds are formed to make different molecules. For example, the bonds of two water molecules are broken to form the hydrogen and oxygen. Energy is always required to break a bond, which is known as the bond energy. While the concept may seem simple, bond energy serves a very important purpose in describing the structure and characteristics of a molecule. It can be used to determine which Lewis dot structure is most suitable when there are multiple Lewis dot structures. Here are some less common applications of combustion of alkanes. For example, mixture of butane and isobutanes are used in disposable cigarette lighters. Similarly, mixture of C5 to C6 alkanes is used in charcoal lighter fluids. Halogenation is the replacement of one or more hydrogen atoms in an organic compound such as alkane by a halogen atom. Unlike the complete transformation of combustion, the halogenation of an alkane appears to be a simple substitution reaction in which a carbon-hydrogen bond is broken and a new carbon-halogen bond is formed. Reaction of alkanes. So the reaction of alkanes with halogens in the presence of sunlight or heat is called halogenation, in which hydrogen atoms of the alkanes are replaced or substituted with halogen atoms. Not all the halogens react same with a particular type of an alkane. Fluorine reacts too vigorously even at low temperatures. So the reaction of fluorine with halogen is called fluorination, and the fluorination is too fast to be controlled. The reaction of an alkane with chlorine occurs when a mixture of two is irradiated with ultraviolet light. Alkanes also react with fluorine and bromine. Reaction with fluorine is vigorous, and whereas with the iodine is reversible. When a mixture of methane and chlorine are subjected towards ultraviolet radiation, first methyl chloride or chloromethane is formed. The reaction does not stop at this stage. Depending upon the time and the concentration of chlorine, the remaining three hydrogen atoms of methyl chloride can be successively replaced with chlorine atoms. Since only two covalent bonds are broken, that is, the first one is the CH or the sigma bond between the carbon and hydrogen of the methane and the bond between the chlorine. And the two covalent bonds are formed, that is a bond between a carbon and chlorine atom and a bond between hydrogen and chlorine called the hydrochloric acid. This reaction seems to be an identical case for the mechanistic investigation and speculation. However, one complication is that all the hydrogen atoms of an alkene may undergo substitution, resulting in a mixture of products that I will show you in the coming slides. The relative amount of the various products depends upon the proportion of the two reactants used. In the case of the methane, a large excess of hydrocarbon or methane favors the formation of methyl chloride as the chief product, whereas an excess of chlorine gas favors the formation of chloroform and carbon tetrachloride. When a mixture of methane and chlorine are subjected to UV radiation, first methyl chloride is formed. If one is using an excess amount of chlorine gas and a prolonged duration of UV radiation, then methyl chloride further reacts with chlorine and dichloromethane and hydrochloric acids are produced. Reaction does not stop at the dichloromethane stage if chlorine is used in an excess quantity. Dichloromethane reacts again with chlorine and forms the chloroform and hydrochloric acid. The chloroform then again reacts with chlorine, and in this way all the four hydrogen atoms of the methane are substituted with the four chlorine atoms, forming carbon tetrachloride and hydrochloric acid. Chlorine reacts with alkanes in the similar fashion but with less vigorously. It means the speed of the reaction with chlorine is faster than the reaction with bromine. As I have already told that the reaction with chlorine is too vigorous to be controlled. However, the reaction with iodine is very slow and is reversible. Here you may see that when methane and iodine are made to react under sunlight, methyl iodide is formed, which again is decomposed into methane and iodine. Now let us discuss the mechanism of halogenation. Halogenation of alkanes comprises of three steps. The first step is the initiation step. It is the homolytic cleavage of a covalent bond of halogen atoms that generate the free radicals of halogen. Here in this case, you may see that a molecule of chlorine is homolytically cleaved with the help of heat or light to produce the two free radicals of chlorine. In the case of methane molecules, the carbon-hydrogen bonds are low-polarity covalent bonds. The halogen molecule has a non-polar covalent bond. UV light contains sufficient energy to break the weaker non-polar chlorine-chlorine bonds having a bond energy of 58 kilocalorie per mole. But it has insufficient energy to break the stronger carbon-hydrogen bonds in methane, which have a bond energy of 104 kilocalorie per mole. Once the homolytic cleavage of halogen atoms takes place, thus generating the free radicals of halogens. A free radical is an atom or a group that contains a single unshared electron. These free radicals, the bond is then ruptured, is said to have broken in a homolytic fashion. Here in this slide you may see that the light is homolytically cleaving a molecule of chlorine. This initiation step is called the initiation step. This first step in which the radicals are formed is called the initiation step. The chlorine free radicals that form are in high energy state and react quickly to complete their octet and liberate energy. Once the high energy chlorine free radicals are formed, the energy source, that is the UV light or heat, can be removed. The energy liberated in direction of free radicals with other atoms is sufficient to keep the reaction running. Once the initiation step has taken place, either with the help of heat or sunlight, thus generating free radicals, when a chlorine free radical approaches a methane or any other alkane molecules, a homolytic fission of carbon-hydrogen bond takes place. The chlorine free radical combines with the liberated hydrogen free radical to form hydrogen chloride, and a methyl free radical is again generated. This is called the propagation step. So the propagation step, in the propagation step, one free radical is consumed and another free radical is generated. A step in which both a product and the reactive species which keeps the reaction going are formed is called the propagation step. So here you may see that in the second step, a chlorine free radical attacks on the methane molecule, generating a methyl radical. This methyl radical will then again attract another chlorine molecule, forming methyl chloride and chlorine radical. This is another propagation step. A second propagation step is possible. In this step, a methyl free radical reacts with a chlorine molecule to form chloromethane, and a chlorine free radical is again generated. When a reaction occurs between free radicals, a product forms, but no new free radicals are formed. This type of reaction is called termination step because it tends to end the reaction. There are several termination steps in the chlorination of alkane. For example, In the termination step, both the halogen free radicals can combine together, generating a neutral halogen molecule. Similarly, the alkyl radicals generated in the propagation step may combine to form another molecule of alkane. It is again a termination step. Similarly, an alkyl or halogen radical can combine to form a neutral molecule such as methyl radical combined with chlorine free radical to form the methyl chloride. It is a termination step. So in the termination step, free radicals generated in the propagation steps combine together to form the neutral molecules without the birth of any other free radical. So the termination step leads towards the cease of the chemical reaction. If only one of the hydrogen atoms gets substituted, it is called monosubstitution. Just to show that things are not always as straightforward as they seem. For example, let us consider the chlorination of butane. If we perform the halogenation of butane with low concentration of chlorine, then if we talk about the statistical distribution of the product, then 1 chlorobutane should be expected in 60% yield, whereas 2 chlorobutane is expected in 40% yield. However, experimentally, 2 chlorobutane is obtained in 71% yield and 1 chlorobutane is obtained in 29% yield. What is the reason of high concentration of 2-chlorobutane, although its statistical distribution is lower than 1-chlorobutane? This needs some explanation. Let us discuss why 2-chlorobutane is obtained in higher yield than 1-chlorobutane. Why 2-chlorobutane is found in higher yield than 1-chlorobutane? The answer to this question is hidden in the relative stability of alkyl radicals. If we talk about the relative stability of primary, secondary and tertiary alkyl radicals, then always remember that just like the carbocations, tertiary radical is more stable than the secondary radical, and the secondary radical is more stable than the primary radical, in which the carbon bearing the unpaired electron is directly attached with one alkyl group, whereas the least stable is the methyl radical. Why methyl radical is the least stable and the tertiary radical is the most stable radical in this series? The answer to this question is the hyperconjugation and the resonance of the unpaired electron. The unpaired electron in the case of free radical is not localized on the carbon atom. In the case of tertiary radicals, the carbon bearing the free electron, unpaired electron is directly attached with the 3 carbons, which are in turn attached with the hydrogen atom. So the hyperconjugation takes place and the tertiary radicals have more hyperconjugating structures than the secondary radicals. Whereas in the case of methyl radicals, there is no effect of hyperconjugation or resonance, and the unpaired electron is fully resides on the carbon atom, and hence it is the most reactive and the most unstable in this series. Similarly, if an aromatic ring is directly attached with a carbon atom that is bearing the unpaired electron, it will increase its stability. This stability, increasing the stability, is due to the increase in the resonance and the stability of the unpaired electron. As I have already informed you that the incorporation of an aromatic or unsaturation bond to the carbon-bearing unpaired electrons increase its stability. Why the aromatic or the double or triple bond increase the stability of radicals? The answer to this question is the resonance, is the delocalization of the unpaired electron over the aromatic or the unsaturated bonds. in addition to the hyperconjugation. So in the case of benzyl radical, if we compare the stability of benzyl radical with the tertiary radical, the stability of benzyl and the allyl radicals are almost equal because of the extensive resonance and hyperconjugation of unpaired electron over the benzene and the allyl group. Whereas in the tertiary radicals, only hyperconjugation counts for the stability of tertiary radical. Whereas in the case of benzyl and allyl radicals, resonance effects are the additional factor that counts the stability of the aromatic radicals. So the question was that why 2-chlorobutane is formed in high yield although its statistical distribution is low. The answer is that the formation of 2-halobutane or 2-chlorobutane proceeds through a more stable secondary free radical, whereas the formation of 1-chlorobutane proceeds through less stable primary radical. That is why the 2-chlorobutane is formed in higher yield than the 1-chlorobutane. When performing the halogenation of ethyl benzene, the substitution will preferably take place at the benzylic carbon. So benzylic substituted product is the most favored product. Benzylic and allylic radicals are even more stable than the tertiary alkyl radicals. It should be easy for a halogen radical to abstract a benzylic or allylic hydrogen through the formation of the more stable intermediate free radical. If we perform the halogenation of propene, halogen atom will replace the hydrogen atoms of carbon 3 and preferably 3 halo-substituted propene will be formed. Why? The answer is that the substitution at the third carbon of the propene produces the more stable intermediate free radical that is stabilized by resonance. So the allyl radical, there is a greater likelihood that the halogen will act electrophilically to the adjacent double bond, rather than on the carbon atoms that are bonded together through a double bond. One very important question arises: what is the relationship between the reactivity and the selectivity? As we know that if we compare the reactivity of chlorine and the fluorine free radicals, chlorine free radicals are much more reactive than the bromine free radicals. So the reason is that the chlorine radicals can easily be formed and generated and have weaker chlorine bond than the bromine bond. However, this very reactive position of the chlorine atom will make it very poor selective, and it will attack blindly with any of the hydrogen available on the alkane. So the chlorine, because of its high reactivity, will react blindly to any hydrogen to which it will encounter. On the other hand, the bromine free radicals are less reactive and more selective. They tend to react preferentially with the east target, that is the tertiary hydrogen, and will lead towards the formation or the generation of more stable free radicals. This property is absent in the case of chlorine, which is more reactive and less selective. However, bromine is less reactive and more selective and give or produce preferably the more stable intermediate free radicals. N-bromosuccinamide is a very good brominating reagent. It brominates the organic compounds through free radical mechanism. Under sunlight or heat, N-bromosuccinamide produces the bromine free radicals in low concentration, which then brominate the substrate. In the case of cyclohexane, it is brominating the cyclohexane at the carbon which are adjacent to the carbon-carbon double bond. First, cyclohexene upon bromination with n-bromosuccinamide is converted into 2-bromocyclohexene and the n-bromosuccinamide is converted into succinamide. If the resonance hybrid of a free radical is symmetrical, more than one products are formed. For example, let us discuss the bromination of 1-butene. When 1-butene is made to react with the free radical of bromine, here I am showing a reaction between the free radical of bromine and a neutral molecule of 1-butene. The bromine will abstract the proton from the allylic carbon, that is from the carbon number 3, thus generating an intermediate free radical that undergo resonance and form the two resonance hybrids that are shown above in this slide. Hence, now the bromine has a chance to get attached either at the carbon number 1 or at the carbon number 3. There are the equal number of chances for the bromine to get attached on the carbon number 3 and carbon number 1. However, the radical in which the free radical of 1-butene in which the free radical or the unpaired electron is on carbon number 3 is a secondary radical, whereas in the case of the electrons on carbon number 3 it is a primary radical. So 3-bromo-1-butane will be formed preferably and the 1-bromo-2-butene will be formed in low concentration. Cyclic alkanes react with halogens in much the same way as the acyclic compound. For example, the halogenation of cyclopentane, all the hydrogens are equivalent and hence any of the hydrogen is replaced will generate the chlorocyclopentane. Cyclopropane undergo electrophilic addition reactions much like an alkene. So the cycloalkane behaves like an alkene and it gives the addition reaction. For example, when cyclopropane is made to react with hydrochromic acid, addition of the hydrogen and the bromine of the hydrochromic acid takes place to the cyclopropane and we obtain bromopropane. Similarly, chlorine gets added into the cyclopropane in the presence of flavorous acids such as trichloride and 1,3-dichloropropane is obtained. Similarly, hydrogenation takes place in the presence of nickel catalyst at 80 degrees centigrade and N-propane is obtained. From the initial reactions of alkanes, the question comes why cycloalkane is behaving like an unsaturated alkane, that is like alkene and alkynes. The answer is that the bond angle in the cyclopropanes are about 60 degrees, which is considerably smaller than the ideal 109 degree. The sp3 hybrid orbitals cannot overlap head to head. The bonds are weaker than the normal bonds. Consequently, 3-member ring undergo ring opening with electrophilic regions, and hence cyclopropene gave addition reactions with halogens rather than the substitution reactions. Free radical mechanism is responsible for the detoxification of alkanes into alcohols. Alkanes are toxic then if we compare it with alcohols which are relatively non-toxic. This conversion of alkanes into non-toxic alcohols takes place in liver via free radical mechanism. An iron-containing enzyme called cytochrome P450 catalyzes this reaction. So, alkanes in the living organisms are converted into a relatively non-toxic alcohols in liver with the help of P450 cytochrome enzyme. Another example of free radical reaction in biological systems involves the reduction of ribonucleotide to a deoxyribonucleotide. The conversion of ribonucleotide to deoxyribonucleotide takes place through free radical mechanism. Aging of human skin is believed to be the product of free radical reactions. Protection from free radical reactions is possible if a compound is present that reacts with radical and forms a less reactive radical. For example, hydroquinone reacts readily with any free radical and is converted into a semiquinone. And this semiquinone further reacts with another free radical, alkyl radical, and is converted into quinone. That is why hydroquinone is a major component of many of the tropical creams. Tropical creams protect you from the sunlight, and this sunlight may cause the free radical reaction in your skin, and ultimately your skin is aged. So anti-aging creams involve the use of hydroquinone. Ozone is a major constituent of smog in the stratosphere. A layer of ozone shields the Earth from harmful solar radiation. The ozone layer is thinnest at the equator and thickest in the polar region. Previously, human beings have used the chlorofluorohydrocarbons as the refrigerants. These refrigerants, upon leaking from the refrigerators, are escaped into the stratosphere, where they start a chain reaction and destroy the ozone layer. And hence, the destruction of the ozone layer is the result of a chain of free radical reaction. A chain of free radical reactions started at the stratosphere are the responsible for the destruction of the ozone layer. Chlorofluorocarbons are exceptionally stable, but under intense ultraviolet radiation present in the stratosphere, they undergo a radical dissociation. So the resulting free radicals produced by the dissociation of chlorofluorocarbons, they start the decomposition of ozone layer. When alkanes are heated with concentrated nitric acid at elevated temperature, the hydrogen of the alkanes are replaced or substituted with nitro group. This is called the nitration of alkanes. The nitration of alkanes produces the nitroalkane. For example, when methane is heated with concentrated nitric acid at 400 to 500 degrees centigrade, nitromethane is formed. So the nitration is also a substitution reaction. When alkanes are heated with fuming sulfuric acid at moderate temperature, the hydrogens of the alkanes are replaced with HSO3 group, and this is called sulfonation. As a result of sulfonation of alkane sulfonic acids are obtained. Alkane sulfonic acids are important constituents in the laundry and detergents. The cleavage of carbon-carbon bond or carbon-hydrogen bond under the influence of heat is called pyrolysis. In simple words, it is cleavage of long-chain carbon chain molecules by heat. The reaction is carried out by passing the alkanes through a chamber heated to high temperature ranging from 400 to 450 degrees centigrade in the presence of catalyst and in the absence of oxygen. The heat energy provided breaks the carbon-carbon or carbon-hydrogen bond, generating highly reactive free radicals. These free radicals subsequently combine with other free radicals to form a series of new hydrocarbons. Pyrolysis reaction is very complex and requires special conditions to control and proceed to a particular desired product. Dehydrogenation is the removal of hydrogen from the alkane molecule. Benzene and other aromatic hydrocarbons are prepared from petroleum hydrocarbons. For example, n-Hexane upon dehydrogenation at 500 degrees centigrade with chromium oxide produces the benzene. The conversion of long-chain aliphatic hydrocarbons into aromatic hydrocarbons with the same number of carbon atoms is called reforming. The chemical reaction is carried out under a high pressure and temperature in the presence of a catalyst. Reforming is utilized in petroleum industry to increase the yield of low boiling point fractions, for example gasoline. Another important contribution of catalytic reforming is the synthesis of aromatics. Aromatic molecules are better fuel and are precursor for various chemical industry. Summary of the today's lecture is that alkanes are non-reactive molecules which react only under the vigorous conditions. Alkanes upon complete combustion produce carbon dioxide and produce energy. Alkanes react with halogen in the presence of sunlight or heat through free radical mechanism. Among the halogens, the order of reactivity is that the chlorine is more reactive than chlorine, and the chlorine is more reactive than bromine, and the iodine is the least reactive. Alkanes react with concentrated nitric acid and concentrated sulfuric acid to afford the nitration and sulfonation products. The order of stability of radicals is that the tertiary radical is free radical is more stable than the secondary, and the secondary free radical is more stable than the primary free radical. Among the free radicals, methyl radical is the least stable free radical. At the end of this lecture, now it's time for a quiz. Compare the reactivity and selectivity of substitution reactions of 3,3-dimethyl butene with chlorine and bromine under the free radical condition. Your answer should address why some products are formed in high yields and others are formed in low yields. So you have to react the chlorine in one reaction with 3,2-dimethyl butene, and in another chemical reaction you have to react the 3,2-dimethyl butene with bromine. In these two reactions, different types of the products will be formed. You have to predict what kind of product will be formed in high yield and what will be formed in low yield, and you have to elaborate your answer why a specific product is forming in high yield and in another reaction the same product is forming in the low yield. So best of luck. Here is the list of suggested books: Introduction to Organic Chemistry from John Wiley and Sons, 3rd edition, 2005. Or you may also consult Textbook of Organic Chemistry written by Muhammad Yunus, produced by the Ilmi Kitab Khana, Urdu Bazaar, Lahore, 2006 edition. Thank you very much.